When light is incident on the surface between two materials, some of the light is reflected and some is transmitted. R represents the ratio of the intensity of the reflected to the incident light, so it's the percentage of light that gets reflected, while T is used to represent the intensity of the transmitted to the incident light, or the percentage of the light that is transmitted. These two ratio percentages should add up to 1 because the sum of the amount of light that is reflected plus the percentage of the light that is transmitted should add up to 1. If we have the special case where light is incident normal to the surface, so that means the incident angle is 0, the light is coming directly downward perpendicular to the surface, then we can use this formula which involves the index of refraction of the original material and the material that the light could be transmitted into or is reflecting off of. The difference between those index of refractions divided by the addition of those two indices of refraction, that ratio squared. So we do have a formula for calculating what R is based on the indices of refraction for that one special case of an incident angle of 0. Now, when you have light which is going from a high index of refraction material to a low index of refraction material, so say from water or glass to air, in that case, you can have what is called total internal reflection. So if we imagine light coming from some light source in the water and heading towards the surface of the water, so we have air up here, water here, the light will bend away from the normal when it goes from water into air. If we make that angle bigger, then the angle of refraction will also get bigger, and it will get larger and larger until at some point the angle is 90 degrees and the beam that is refracted will be just skimming along that surface. When this happens, when you get this angle of refraction being 90 degrees, the incident angle is known as the critical angle. Any higher than the critical angle, an angle that's bigger than the critical angle, will result in total internal reflection. None of the light will escape into the air, into the material with the lower index of refraction. All of it will be reflected back into the original material. So we can analyze this situation using Snell's law. So if you have the light going from the high index of refraction material to the low index of refraction material, so say like water to air, then N1 will be that higher index of refraction material, and the theta 1, the incident angle, is going to be this critical angle. And so if that's the critical angle, then N2 will be the index of refraction of the low index of refraction material, and sine of theta 2, well, theta 2 is going to be 90 degrees, and the sine of 90 is just equal to 1. So we can rearrange this equation to find out what that critical angle is. So the sine of that critical angle will be the ratio of N2 over N1, the low index of refraction material over the high index of refraction material. And if you happen to get these two mixed up and put the high index of refraction on top of the lower one, if you take the inverse sine of that, your calculator will yell at you and won't let you do it. So the low index of refraction material always goes on top because that gives you a valid angle. So the critical angle is smaller for high index of refraction substances. And this is significant because it means if you have a material with a high index of refraction, then the critical angle is small, which means there's a wide range of angles that will undergo total internal reflection. One application of this is in fiber optics. So fiber optics are long, thin, very thin cylinders made of a high index of refraction material, usually glass or sometimes plastic. And internal reflection, since it's a high index of refraction material, most angles will totally internally reflect. And so these internal reflections make the fiber a pipe for light. They carry the light from one end of the fiber to another. So here we can see a fun decoration where you have some colored lights in the base, and then the decoration, these fiber optics, carry the light outwards. You may have seen Christmas trees that use fiber optics to light up some of the pine needles. Another application of fiber optics is with the endoscope. So an endoscope allows doctors to see inside the esophagus and inside the stomach. And so with an endoscope, you have some way of viewing the inside. So you have some optics down here which capture an image of the inside of the stomach. The light from that image gets carried by the fiber back up to the other end of the endoscope that the doctor can look in and see the inside of the digestive tract. So in addition, there's going to be a light that shines down the other way and goes into the stomach to illuminate it. And there's also the possibility for other instruments to be passed along near the fiber in order to take a biopsy if the doctor sees something that looks troubling. So the endoscope makes use of fiber optics to carry images of the inside of a person's body without having to cut a hole in them.